In this video we are going to start exploring the properties of the notion of parallel transport that we have introduced in the previous video. One of the main uses of parallel transport in Rn was the construction of parallelograms. So how did we do that? Here we are always talking about infinitesimal parallelograms and infinitesimally closed points. So if I don't say it all the time, you have to remind yourself that I am talking about that. So first you choose a base point P, and at that base point you choose two vectors, psi mu and eta mu. You can view these vectors as connecting two infinitesimally closed points. So in this case would be Q and P, and in this case S and P. In other words, what we are saying is that the difference between the coordinates of the point Q and those of the point P are this vector, and this thing behaves as a vector with origin in P, and x mu of S minus x mu of P is eta. So this is the starting situation, and you construct the parallelogram now by taking eta mu and parallel transporting it along psi mu to Q. The result would be a parallel vector eta prime mu with origin in Q, and then you would do the same with psi mu along eta. The result could be some other vector psi prime mu. And I'm already drawing the parallelogram in this way, which is not really what it looks. A parallelogram looks like in Rn. It is not a closed figure because we don't know with the notion of parallel transport that we have, this is going to close or not. So how can we find out? This point here, let me call it R, will be just the coordinates of that point would be the coordinates of x at P plus x mu plus eta prime mu. So we write it like this. Would be x mu of P plus psi mu plus eta prime mu, while the coordinates of this point that I call R prime and that could or could not coincide with R will be the coordinates of the starting point, also P plus eta mu plus psi prime mu. Then the question is whether these 2 points R and R prime are the same, and if our coordinates are good coordinates, then two different points which are different will have different coordinates. So we just have to compute x mu of R minus x mu of R prime. Clearly the coordinates of P drop from this calculation, and we have psi mu plus eta prime mu minus eta mu plus psi prime mu, which we can reorder as eta prime mu minus eta mu minus psi prime mu minus psi mu. And remember that eta prime mu was obtained from eta by parallel displacement, and psi prime was obtained by from psi by parallel displacement. So the only thing that survives here is the vector. Remember how this was defined as minus. Here was delta, and this delta was the vector of the displacement, which here is psi. So it will be psi rho gamma rho mu sigma eta sigma. And here you have same sign. Now the vector of the displacement is eta rho gamma rho sigma mu psi sigma. You can since we have gamma and gamma, we can write this in this way, of sigma mu psi rho eta sigma minus eta rho psi sigma. Okay, this is just minus 2 times psi rho eta sigma antisymmetrized. This factor of 2 takes care of the 1/2 that we introduced in the antisymmetrization with weight 1. So we re-express this, sorry, the minus sign was from here. So it is minus 2 gamma rho sigma mu psi rho eta sigma. Now, because this is antisymmetric and is contracted with these indices, only the antisymmetric part survives. And the conclusion of this calculation will be that R is equal to R prime if this object, for any psi and eta, if this object vanishes. This object is called the torsion, with its indices it will be rho, sigma, and mu. Let's put the definition here. And it is the antisymmetric part of the connection. How does this object transform? You might expect that naively that since gamma is not a tensor, T will not be a tensor. But let's check it. So T prime mu nu rho really is like minus 2 gamma mu nu rho prime. Now, apart from the factor of minus 2, okay, there is this famous homogeneous term, which is the term that corresponds to any tensor. Okay, just Jacobian and inverse Jacobian matrices multiplying gamma. So that term would be fine with a tensor. The real question is what happens with the inhomogeneous term. This inhomogeneous term was J rho lambda partial with respect to y mu of J minus 1 lambda and nu. So this is the term that appears in the transformation of gamma. Now you have to subtract the same term but with mu and nu interchange. This is expressed in this way. The symmetrizer, antisymmetrizer, introduces a factor of 1/2, but this factor cancels with the factor of 2 here. Okay, and the only thing that we have to take care of is this factor of minus 2. But since we wrote the minus 2 here, really I need this factor of 1/2. It is not relevant, because now we want to see what this is. Remember that J minus 1 lambda is x dx lambda dy nu, and we are saying that we are taking a further derivative with respect to mu. Okay, so this would be d2 lambda dy mu dy nu. But now we are going to subtract a term of the same form with mu interchange with nu. But since this covariant, partial derivatives, second partial derivatives commute, then this term would cancel with the analogous term here. Okay, this comes multiplied with J rho lambda, but really doesn't do anything at all. The antisymmetrization only concerns these two terms, and this is an overall factor. So this term, this inhomogeneous term, vanishes in this particular case. Only the homogeneous term survives, and the torsion tensor is a tensor. Okay, an important tensor. There's another way of obtaining this tensor, which is very interesting and simple, and which also helps you to prove that it transforms as a tensor, in spite of the fact that it depends in this way from the connection. This way consists in computing the a commutator of two covariant derivatives acting on a scalar function. So we have to compute this minus another term with mu and nu interchanged. I don't write it, and this is a typical expression in which that you use many times, just because it is very convenient. Okay, we'll see that how it works. Okay, so it's nabla mu acting on partial nu f, because the covariant derivative acting on scalar is just a partial derivative. And in any case, this is a covariant vector, and if we apply the covariant derivative, there is the partial derivative, there is a minus term, gamma nu rho partial rho f. Okay, the index of the derivative is the first index in the connection. If it is a covariant tensor, then this second index is the index of the covariant tensor, and then the one which is contracted with the components of the covariant tensor is the upper one. Minus mu interchanged with nu. But you see that because the two partial derivatives commute, this term will disappear, and you will get two terms like this. So minus gamma mu nu rho partial common factor partial rho f minus gamma nu mu rho partial rho f. This is just 2 times nu rho. And this is what we have defined as the torsion. And because the partial derivative is the covariant derivative, we re-express it this way. And let me write this identity here. It's a completely general identity for any f and for any connection. This kind of identities, which tell you what the commutator of two covariant derivatives acting on tensors are called Ricci identities, and this is the simplest one, because the tensor on which we are acting is just a scalar. But now this has this virtue. F clearly is a tensor. Scalar is the simplest tensor. The covariant derivative produces tensors. The commutator of two covariant derivatives is just a subtraction of one tensor and another tensor, so this is a tensor. The covariant derivative of f is a tensor, so it's obvious that this has to be a tensor. Okay, and you don't need to prove that it is a tensor studying the transformation of T mu nu rho explicitly. Okay, we will see more Ricci identities. This is the simplest. In this one only the torsion appears, but in the rest of the Ricci identities there will be another element that we are going to study now. The next thing that we can do with this rule of parallel transport is to study this situation. Okay, we start from a point P as usual with a vector which is defined here. This is not a vector field. This is not the result of evaluating a vector field at the point P. It's just, or could be, but it doesn't really matter. It's just a vector defined at that point. And there are other points. Okay, let me give them names Q, S, and R. So this will be what I call delta x mu. Okay, delta x mu, and this is what I call delta y mu. And this S is defined by the fact that the vector or the increment that connects Q with S is delta y mu, and this is delta x mu. Okay, in this case, this is something that really closes. It is not a parallelogram in the sense that we defined before, because I am not parallel transporting a vector from here to here. This is just an increment of coordinates, delta y mu, okay, and some displacement, and I just apply it from Q to S. I don't care if it is parallel transported or not. Probably it is not. Then what I want to find out is what happens with the original vector psi mu, which is defined at P, if I parallel transport it from P to Q, from Q to S, from S to R, or from R to P. A simpler way of addressing this question is, okay, if I just transport it to S, but first I do it along this route that I will call the upper route, and then along this route that I will call the lower route, will I get the same result? Okay, this is the same as asking if I go around this loop completely from P to P again, psi mu of P will be parallel transported to psi mu of P again or to something else. These two questions are clearly the same. Okay, it's just that going from P to S by two different ways is simpler to compute, and the result is can be written in a more interesting way. So first I transport it from P to Q. This means that I get what I will call psi Q mu, and by definition this is psi mu P minus delta x rho gamma rho mu sigma psi sigma P. Okay, now I am going to go from Q to S. At what I call what I get, I will call psi S mu, and let me call it upper, because I am getting the vector at S from Q and not from R. So this will be psi mu Q minus, now the displacement is delta y rho, psi rho sigma mu psi sigma Q. Okay, one observation is that when I do this displacement, I evaluate the connection at P. Let me call this coordinate X. But when I do the second displacement, the second parallel transport, then I have to evaluate gamma at Q, whose coordinates are X plus delta X. Okay, so I have to take that into account. And one last warning, maybe I should have said this before, but delta x mu and delta y mu do not refer to different coordinate systems. We are always working in one coordinate patch unless we say that we are going to change coordinates. And maybe I should write this. Delta x mu is x mu of Q minus x mu of P. Delta y mu is x mu of R minus x mu of P. Okay, where these x mu's are the coordinates in our coordinate patch, and these differences I call delta x mu and delta y mu just because it is convenient. Okay, now the thing is that this psi mu Q that I have here has been computed before, so I can just substitute the result. And I will do it here. I get psi mu P minus delta x rho gamma rho sigma mu at x psi sigma P, and then I have this second term, okay, minus delta y rho, and let me expand this in Taylor series. Okay, so this would be gamma rho sigma mu at x plus delta x, say alpha, partial alpha gamma rho sigma mu evaluated at x, and this multiplied by psi sigma q, and this is again psi sigma p minus delta x rho gamma rho sigma and say beta psi beta p. Okay, this is the result. In this case, if I stay at first order in this infinitesimal displacements delta, I will show that I get nothing. So I am going to stay to second order in these displacements, which are, as I said from the beginning, meant to be infinitesimal. Okay, so these two terms suffer no modification. I just have to copy them. I don't write the argument x anymore, because after the expansion everything is defined at x. Everything, I mean the connection. Psi sigma p minus, and now I multiply gamma by this term and then by the second term. So first delta y rho gamma rho sigma mu psi sigma p, then minus, and minus will be plus delta y rho. I put this delta x rho. I have to change the index here because I am using rho here already. So let's call rho lambda. So delta x lambda gamma rho sigma mu gamma lambda beta sigma, and then psi beta. And now I have to multiply this term by this. It's minus delta y rho delta x alpha partial alpha gamma rho sigma mu psi sigma p. And the next term would be this multiplied by this one, but this has 3 deltas, so to second order in delta, this is all we have. Okay, now we are interested in computing psi mu upper minus psi mu s lower. So this are the vectors. So the psi mu lower would be the same but obtained along this lower path. But the only difference between the upper path and the lower path is the order in which I take these displacements delta y mu and delta x mu. So really what I have to compute is this, which I have already computed, psi s upper minus whatever I get by interchanging delta x and delta y. And let me inspect psi mu s upper and see what how the terms depend on delta x and delta y. The first term here is independent of delta x and delta y, so it will have the same form. Since I am subtracting, this term will drop from the difference. Now consider these two terms, and you see that the first term and is the second term with delta x replaced by delta y. So when I consider those two terms, I get something which is invariant under the replacement or the interchange of delta x, delta y, which is symmetric under that replacement. So if I subtract what I obtain by replacing delta x by delta y, I am subtracting the same term, so they will cancel. And the terms that it's not clear whether they will cancel or not are this one and this one, and I'm going to write them in more detail. So these are the terms that maybe will survive, and let me start with this one. Okay, I will do it step by step. So first, this is what we got from the beginning, rho sigma mu and psi sigma p. Then I will have to subtract a term that I obtained by replacing delta y by delta x. But this is the same as abstracting a term that I obtained by replacing rho with alpha. Just think about it, it's the same as interchanging here these two things. So I interchange the indices, and well, the result is the same as if I antisymmetrize and multiply by 2. Remember that the antisymmetrizer has a factor of 1/2. Okay, so I have to compensate that with a factor of 2. That would be the only thing that survives here. If this is antisymmetric, okay, then only the antisymmetric part of this will survive. So this is automatically antisymmetrized. Now let's consider the other term. Okay, you see that I am going to do the same reasoning. And that the only effect of subtracting the term a term with delta y and delta x interchange is that I antisymmetrize and I multiply by 2. This is the result, but I need to massage it a bit. I want to take this psi p, as a common factor, so I change the sigma by beta. Okay, and then psi beta will be a common factor. Then just by convention, I am going to write this as minus delta x alpha delta y rho 2 times, okay, so this corresponds to the first term. I have done nothing, okay, this is exactly the same. And here I need to call this lambda alpha. So I just do exactly the same. And I will get minus, because I am using this minus here in the front, gamma rho sigma mu gamma, and now instead of lambda alpha, beta sigma psi beta p. One last thing, okay, remember that this is antisymmetrized. I didn't say it before, but because this is antisymmetric here in rho and lambda, this is automatically antisymmetric in rho and lambda. Okay, just because here we have this order alpha rho, then I want to have the same order here. Okay, so let me write the final result in this way. And now I have a plus alpha sigma mu rho beta sigma psi beta p, and this is basically the result. So you see that the result of parallel transporting a vector from one point to another along 2 different paths is different. If and only if, in general, if this object that appears here multiplying the vector and these displacements, and an object that has these indices vanishes. This object that appears here is the curvature. Okay, as I define it in terms of this function of gamma, it is a 1,3 tensor. Well, and I have said tensor, but if you look at this definition, you will say, oh my god, gamma the connection is not a tensor, and I have products of something which is not a tensor, and partial derivatives, not even covariant derivatives of something which is not a tensor. So chances are that this will not be a tensor. Well, you can prove that this is a tensor, and you can do it in 2 different ways. The hard way, which is just computing the transformation but brute force, or you can use one of these rich identities. Which one? Well, the next one which is the identity that tells you what is the result of acting with the commutator of two covariant derivatives on a contravariant vector. So let us compute this. This is just the definition. Okay, and how do I operate with this? Well, I should start by expanding this covariant derivative. It is a covariant derivative acting on a 1,1 tensor. So first I have the partial derivative. Then if I take the derivative with respect to this upper index, first, then it is a plus a gamma with the same index as the derivative. Then the upper index that we are considering now, and some index to contract the result, and this is now the tensor. Then there is another term, but now with a minus sign, that takes care of the lower index. Again, the first index is the same index as the derivative. This is the way to remember. The second index is the index of the tensor, and now this is the index that is going to be contracted, and this is left untouched. Okay, now we replace the values of these covariant derivatives, which are known to us. These are easy to compute, so we have partial mu, then the first term, plus partial mu of the second term, which is this one. Okay, I'm going a bit faster, but you should already know more or less how this goes. We have mu sigma alpha, and there is the partial derivative, and there is also the term with gamma mu, sigma, and here delta psi delta. So this takes care of the second term, and finally we have the last term, gamma mu sigma, which I'm going to leave it just as it is, because I forgot. Okay, I forgot. I need to subtract the term with mu interchange with nu, because I am not just computing this, but the commutator. Okay, so minus mu interchange with nu. When I do this in this term, this only affects gamma, and I know what the antisymmetric part of gamma will be, which is the torsion, so I just leave it as it is. Okay, now I can start seeing what happens. First, this term is symmetric in mu and nu, so it will disappear. I can write 0. Just then I expand the partial derivative in two terms. When I consider the antisymmetric factor, I just have to multiply by 2 and antisymmetrize. How about this? This is the second term that comes from here. Okay, I look at the next one. And I see that this, I did it wrong. This should be mu. That these two terms are, one is the symmetric of the other. So both of them, the sum of them, is symmetric in mu and nu. So when I add when I subtract something with the mu and nu, mu replaced by nu, and vice versa, these two terms cancel. And then the next one. Okay, I have no reasons to suspect that it vanishes, but it is antisymmetrized and multiplied by 2. And then the last term is also antisymmetrized and multiplied by 2. Okay. Finally, I want to have a common factor, so let me call delta this index, and you see, comparing with the above definition, that this is just r mu nu delta alpha psi delta plus T mu nu sigma nabla sigma psi alpha. And this is the commutator of nabla mu and nabla mu acting on psi alpha. Okay, this is the second Ricci identity. And as I advanced, it expresses the result of the commutator of two covariant derivatives acting on some tensor in terms of the torsion and some other thing, which in this case is the curvature. This is going to be what happens always. It's the curvature and the torsion and nothing else. And the term with the torsion always has the same form, and it is the torsion with the derivative, covariant derivative of the tensor in question. Okay, now we look at this expression and we see that the left-hand side of the equation is a tensor. Its covariant derivative is acting on a tensor. The second term in the right-hand side is a tensor. We proved that T was a tensor. The covariant derivative of psi alpha is a tensor. And then the first term is a tensor, which is psi delta. Then R mu nu delta alpha must be a tensor. So this proves that the curvature is a tensor, as we said. It is a 1,3 tensor. It is a 1,3 tensor, and it is always antisymmetric in R mu nu, because this is antisymmetric in R mu nu. So R mu nu delta alpha is R mu nu delta alpha, or if you want to express it in a different way, minus R mu delta alpha. Okay, now you can do the same for one form or other tensors, and you will get other Ricci identities. So for one form, we are going to get, and this is more or less a mnemonic rule again, where you had a plus, like here, you get a minus. And where you got a contraction like this, you are going to get a contraction like that. So it will be R mu nu delta, the index here is alpha, and delta omega delta. This is where you are, and then the universal term, mu nu sigma nabla sigma omega alpha. Okay, so this is another Ricci identity. You can act on more complicated tensors, like the metric or whatever, if you act on a general rank R, S tensor. Well, you get R terms of the form R mu nu alpha 1, then an index to sum over delta, which is the index in the position of the index that you have replaced here, alpha 1, then alpha 2, alpha R, beta 1, beta S, plus again another term. Now it's alpha 2, T alpha 1, delta alpha 3, blah 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 blah, and then up to R terms of the same kind, and then terms with minus sign, R mu nu, it is now beta 1 delta T, the upper index is untouched, and the first index is replaced by delta, beta 2, and so on, minus R mu nu, beta 2, delta T, upper index is untouched, beta 1, delta beta 3, beta 3, and so on, plus up to S terms, and then the term which is universal mu nu sigma nabla sigma of the tensor with the same indices. When you write a tensorial identity or equation, you have to have the same kind of indices, not just the number, but also the same indices in the right hand side and the left hand side. Here the three indices were mu, nu, and alphas and betas, and then in the left hand side you have to have, each term has to have the same indices. Okay, so this is the result. And apart from helping us to prove that the torsion and the curvature are really tensors in spite of their complicated form in terms of the connection, is Ricci identities are very useful because they are going to help us prove very important identities, which are called Bianchi identities.